questions. I mean, the worksheet is in the group. I've shared
Okay.
it in the. So so let's start with this one. So the question is, what's a monodentate ligand, right? You can name me properly, right?
Yeah.
So what's a monodentate ligand? It's a ligand that forms one dative bond in a metal complex, or one. Is that clear?
Yeah.
So like water and NH3, right? Again, I told you that you're gonna get typical questions like copper sulfate aqueous, right? So what's going to be formed? The the formula of the complex. So if you add NH3 to it, what are you going to get? You're going to get NH3 4. Uh, maybe two H2Os are left, right? And it's going to have a +2 charge. Sorry, Balki, I have to. If you add a few drops of NH3, so if you go back and have a look at the notes, so you have to remember what happens if you add a few drops of NH3 and what happens. I mean, these were the equations that were given. Where's the ligand exchange? I think this one over here. So I'm just going to repeat everything. Copper sulfate aqueous. To You add OH ends, it will form COH2, right? Pale blue precipitate. You add dilute NH3 to it, and if you add a few drops, what happens is that NH3 initially reacts with the water as a base. It accepts the H coming from water, it turns into NH4+1, and it becomes OH -1. And then the water ligands, they get replaced by the OH ends and they form a pale blue precipitate. And so with ammonia, when you add a few drops, you get copper hydroxide. The ammonia behaves as a base. But when you add NH3 in excess, then the NH3 comes in, starts knocking out the OH, and it's NH3 aqueous, so there would be some water molecules. The number of water molecules, that's up to you. The total has to be 6. So the OH ends are going to get displaced by NH3, but it's going to happen when you add NH3 in excess. So this thing is when you have NH3 in excess. When you add a few drops of NH3, you actually get COH2, right? Is this clear? It's Qasim, is this clear?
Yeah.
Excess of anyways, that's obviously copper hydroxide. Concentrate HCl, it's going to form CuCl4, 2-. The observations are this is greenish yellow. With OH, that's a pale blue precipitate or solid. And the last thing is this one is deep blue. So you got to remember these complexes. These have to be memorized, and all these ligand exchange reactions. And you have to remember the exact same thing for cobalt as well. It's going to be the exact same complexes and the same equations, except for the fact that the colors are going to be totally different. Okay, when water is added, the cobalt 2 chloride, the color of the solution changes from blue to pink. Explain these observations. So it's basically if you change the ligand, why does the color change? That's what the question is. No equation is needed, but you should include references to electron movement between orbitals in your answer. So it's a 3-mark question. They've given you plenty of space. So it's all about why does the color change? And that's exactly written over here. It's because of your D subshells. So we wrote down 2 answers. One was that why are they colored in the first place? And in our case, why ligand exchange changes color of the complex, different ligand lone pairs have different charge density. And hence they exert a different repulsion, and the energy gap delta E created between the d orbitals is also different. So since E is equal to HF, a different frequency from visible spectrum is absorbed, hence a different complementary color is seen. So this is exactly what you're going to write. They specifically told you that no equation is required, right? And so colors was that when the ion forms a complex, the water molecules they come in and they start creating repulsion, and it becomes harder to keep electrons in some of the d orbitals, and it becomes easier to keep electrons in other d orbitals. So d orbitals split, and the energy gap exactly matches frequency. So different ligands will exert a different amount of repulsion, and that is why a different color is seen. Right? Is this clear? Tika, I've sent you notes as well. Remember, most of the questions
Yes.
are going to have exactly the same answer. Okay, when chlorine is bubbled into FeSO4, the color of the solution changes from pale green to yellow. Use data from the data booklet to explain this observation. This is not about transition metals. Yeah, it's more about, we can leave that. Here's a transition metal question. There's a ligand exchange happening, and he's asking you to write down the K-stab expression. So it's going to be product concentration, right? And so product concentration divided by your reactant concentration. Except that you don't write water in the expression because water is in large excess. So you don't write that. Now, they've given, for the above equilibrium, they've given a numerical value of K-stab. So you have a numerical value of K-stab, and it's a low value, which kind of indicates that the equilibrium is not going to actually move forward. The ligand exchange is highly unlikely. So the question is, calculate the concentration of FeH2O6 in a solution in which the concentration, so you basically have to plug in the values. The K-stab are given, that's 0.080. Uh, so FeCl4, that's 0.1. FeH2O6, you don't know. And ClN concentration is 2. 2 to the power 4. Isaac, Qasim, can you tell me what the answer is for X? Okay, all of this is given. So the only thing that's left is X. Can you tell me what the value is?
Well, I'll just go get my calculator.
Okay.
Zero 0.08.
Okay, 0.08, right?
Yeah.
I mean, the answer to this is
Yes.
0.08. I mean,
Wait,
what's X?
X, wait. X is gonna be, yeah, time. Okay, one second. I'll do it again.
It's 0.1 divided by 2 to the power 4 into 0.08.
It's 5/64,
5?
which is 0.078125.
0.07812. So you can just write 0.078, right?
Yeah.
Okay, next one. As I explain what is meant by a transition element. So it's so what is meant by? Remember, in the notes we wrote down the definition initially. It's an element that forms stable ions with incomplete d subshells. With incomplete d subshells. That is what a transition metal is. Basically, transition element is, I told you initially that transition, but let me show you in the notes is just for revision. Right at the beginning, I made a distinction between D block elements and transition elements. These elements over here, they're all D block elements. They're not all transition elements. Transition elements are elements that have certain properties. They've got high melting points, high densities, variable oxidation states, colored compounds, and they are the very good catalyst. So the number one thing is that they have to form colored compounds, and a number of properties depends on that. So the D subshell in their ions, they have to be incomplete. Otherwise, the electrons will not go into excited state. So that is one of the main definitions. It's also written over here. One second, it's going to be written somewhere. Uh, that's the definition. Okay, so it's an element that forms stable ions having incomplete D subshells. So going back to this, um, I mean, we're going to ignore this. This is about electrochemistry, so we ignore that. But we're going to try and do part C. So there's ruthenium, and it forms a complex ion. And one such complex ion, X, ruthenium ion, I'm reading over here. Ruthenium ion has a coordination number of 6. Now, coordination number, I mean, by the word itself, is the number of coordinate bonds it's going to form. So it's an octahedral complex. I mean, 6 bonds, you're going to have octahedral shape. Now, each complex ion X contains one Ru plus ion. So I'm going to, so it's going to contain one Ru plus ion, one Cl ion, one SO2, and the remaining ligands are NH3. So I'm going to have 4 NH3s, right? Because the total coordination number is 6. So one Ru plus is going to have one Cl ion, one SO2, and 4 NH3s. So what is going to be the total charge on this complex? It's going to be +1 and -1. SO2 is neutral, NH3 is also neutral. So it's not going to have any charge. So what is the meaning of the coordination number? It's the number of coordinate bonds formed by the metal ion. And state the formula of X, including its charge. It's not going to have any charge. Is this clear? And the way you should write this is I'm going to put Cl in brackets, I'm going to put SO2 in brackets, and then there would be 4 NH3s. Ru was +1, Cl was -1, and the other two were all, they were neutral, right? TK, is this clear? Ibrahim, Qasim, Isaac, is this clear?
Yeah.
So draw the 2 isomeric forms of X in the boxes below. Your diagram should show the 3-dimensional shapes. So 2 isomeric forms of X. What is X? X, I think. Yeah, he says the SO2 molecule. So he states that the SO2 molecule acts as a monodentate ligand and is attached to the Ru2 plus ion via the sulfur atom. I said just one second, I made one mistake, which was that Ru was actually 2 plus, not +1. So that means the overall charge would be +1. So this thing over here will have a charge of +1. Okay, he says that the SO2 molecule over here, it forms a monodentate ligand and is attached via the sulfur atom. So the sulfur is the one that's its lone pairs are the ones that are attached to the Ru2 plus, and you have to draw the two isomeric forms of this. So remember, it's octahedral. That's the first thing. So one bond on top, one bottom, one right. One is to the left, one is dotted, that's going behind, and then there's going to be a wedge shape, which is going to be coming in front of it, right? And it's going to have two isomeric forms. And let's see what those two isomeric forms are. So this one is octahedral as well. Okay. So we've got the X, Y, and Z axis, the six bonds. Now, remember, there was one SO2, so an E specificity told us, and there was one Cl minus one. And then there were four NH3s, right? So that's one NH3, that's another NH3, that's another NH3. Again, you have to show the N datively bonding to the Ru2 plus that's in the middle. And this is Ru2 plus, right? To be clear, is this clear? This is how it's going to look like. Isaac, Qasim, Ibrahim, is this clear?
Yes, sir.
Yes.
So what's the other isomeric form? The other isomeric form is going to be that in this molecule, the SO2 and Cl are like on opposite sides. So the other one that you're going to draw, the SO2 and the Cl minus one, they would, I mean, you can keep Cl minus one where it was. The SO2, I can bring it right next to it. Instead of being on opposite sides, they're like 90 degrees. And the ammonias are over here. So the difference now is that the SO2 and Cl are right next to each other. So one of them is trans and the other one is cis. To be clear, you've got cis and trans isomers in transition metal complexes. The ligands could be together or the ligands could be on opposite sides. ठीक है, is this clear? Clear है कि नहीं clear?
Yes.
And this is called geometric isomers or cis trans. And explain the origin of the color in a transition element complex such as X. So right now he's talking about the why are they colored, right? So that's your typical answer, which is okay, we'll just read it once more. So the typical answer is why are they colored? So due to repulsion from lone pairs on ligands, D subshell splits into two energy levels. Electrons from the low energy d orbital can absorb energy and jump to the high energy d orbital, goes into excited state, E is equal to HF. So the energy is proportional to frequency, which matches frequencies that belong to the visible spectrum, and therefore you see a complementary color. So that's your, I mean, that question is going to come in every exam. You got 10 questions, the one question would definitely be on transition metals. And if it's on transition metals, they are going to ask you, why are they colored? So over here, I mean, they gave you plenty of lines. It was a 3-mark question. You just have to answer that. Again, define what a transition element is. It's an element which will form stable ions with incomplete desorptions. Now he's asking you to compare the melting and points and density of iron and compare it to calcium. So So the melt, and he's not asking for any explanation. He just wants you to compare. That's it. So melting point and density of iron obviously higher. That's it. You have to write the electronic configuration of Fe. That's 26 electrons. So that's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's 20 electrons, and then 3d6. Now, the 4s is going to be filled first, then your 3d. Now, it lost 2 electrons, right? Fe2 plus. So the outer 2 electrons would be, they're going to be gone. Again, same question. This time it's a 4-mark question. So again, you just write exactly the same answer. Explain the origin of the color in transition element complexes. And remember to differentiate between them. Are they asking for the why are they colored? Or are they asking the question, why do different ligands have different colors? I said this one. There's an excess of CN aqueous added to FeH2O6, and you get this complex, right? Now heating with dilute nitric acid, then neutralizing the product with Na2CO3 produces red crystals which have this thing. So first thing, state the shape of this complex ion. Now this one is going to be, it's got 6 dative bonds, so it's going to be octahedral, right? You have top, bottom, right, left, and front and back. Then he's asking, write an equation for the reaction. So this is about the ligand exchange reaction that happened over here. So your Fe, which was with 6 water molecules, and it had a charge of plus, what was the charge? Plus 2, 2 plus. It reacted with the CN ligands, and all ligand exchange reactions are reversible. So it ended up forming Fe, CN6, and the charge was 4 minus, and the 6 water molecules got knocked out, and 6 CN9s took its place. Now he's asking, deduce the oxidation state of iron over here, which is going to be the same way like normal oxidation state. Cn, you know, is -1. So that's times 6, and the total charge is -4. If you solve for this, take the -6 to the other side, it's going to come out to be +2. Same thing over here. It's going to be x. Cn is -1 times 5. NO has a charge of, it's got no charge. The total charge is -2. So if you solve this, it's going to come out to be +3. PK Ibrahim Qasim Isaac, is this clear?
Yes, sir.
Yeah.
As I define the term monodentate ligand, what's a monodentate ligand? It's a ligand that will form only one dative bond in a metal complex. Uh, he's asking you to show the three-dimensional diagram for FeCN5NO. So you can do that. It's an octahedral complex. So one bond on this side, one on this side. You got it. Okay, so you got 5 CNs. And there is one NO. And the whole thing is going to have a charge of 2 minus, right? Okay, the two complexes are different colors. Explain. So again, it's the same question. Explain why the colors of the two complexes are different. So same thing. It's going to be the same answer, different. Now this time it's 2 marks. The only variation is sometimes it's going to be 2 marks, sometimes it's going to be 3 marks, sometimes it's going to be 4 marks. So they're just looking for, sometimes they're looking for lesser detail. You just write the whole thing. That different ligand lone pairs have different charge density and they exert a different repulsion, which creates a different energy gap when the d substance splits. And since energy is proportional to frequency, a different frequency is going to be absorbed from the visible spectrum, and you would see a different complementary color. So what's the coordination number? It's the number of dative bond formed by the metal ion in a complex. So if he's got a coordination number of 6, so that's the number of dative bonds that are going to be formed. So now we've got, it says that E shows both optical isomers and cistrons. So C2O4 ion is being represented by this symbol over here. So now he's asking to draw the trans isomer and the optical isomer. So the molecule is given over here, E is given. Now this is the cis version because if you look carefully, the Cls are on. I mean, they're on the same side. So we are going to draw the, so I would have to draw the trans version, which is that the Cls, they have to be on opposite sides. And the dotted line, so I've got this ox thing. It's a bidentate ligand, so I'm going to draw it like this. Okay, is this clear? ये clear है सारों को? I
Yes,
had
sir.
Cls and now Cls are on opposite sides, right? The ox was the bidentate ligand, so it was attached on these two sides. Now it's attached on the remaining side, whatever's left. Okay, so that's your cis and trans. The other one is you have to draw the optical isomer. Now remember this, the optical isomer happens when you have bidentate ligands, which is that we did that part right at the end when we were doing, so we were doing bidentate ligands, and I told you this was cis trans. And I told you about mirrored versions. That if you have an octahedral complex and you got bidentate ligands, then the mirrored version is going to be a different molecule. It's going to be non-superimposable, just like your left hand or right hand. They'll kind of look the same, but they will never be superimposable on each other. So we have to draw the mirrored version. Whenever you have bidentate ligands in an octahedral complex, this is what's going to happen. So I'm going to try and draw the mirrored version. So the dotted line goes on this side. So the first thing is I'm mirroring everything. So the Cls are going to be over here and over here, right? So that's mirrored. The ox, which was on the right side, this ox thing will go over here, and this ox over here will be on the, which was on the left side over there, will be on the right side. DK, is this clear that this is the mirrored version? You clear?
Yes.
So now the question is, what's a polydentate ligand? So it's a ligand that can form multiple dative bonds in a metal ion complex. Mono means one, polydentate means it can form many dative bonds with a metal cation in a metal complex. And eta is one such polydentate ligand. So write an expression for the stability constant for equilibrium 1. So this is K stab. So K stab is just your product concentration divided by reactant concentration. There's a ligand exchange happening. you just don't write water in the expression. So it's going to be cadmium with eta. And it's going to be CdH2O6. And eta 4 minus. Make sure one thing that the square bracket represents concentrations. When you write the K-stab expression, put the charge inside the square bracket, not outside it. And you don't write water in the expression. So now I've got this one has to do with the. I mean, there 2, 3, 4. I think all of them are ligand exchange reactions. So write an equation for equilibrium 4 in terms of K-stab 2 and K-stab 3. Now, if you look at equilibrium 4, and let's give it some value, AB. This is A and this is B, 2B. Then it forms C, and it forms 4D. I'm just trying to simplify things because I can't waste time writing the whole thing. So the K equilibrium is basically what? It's C and into D to the power 4, and the whole thing gets divided by A times B to the power squared, right? Yeah, is this clear that I just substitute just to make life easier? I substituted the complex with A, B, C, and D. Is this clear?
Yes.
Achha, now this thing over here is
So it's
A.
just products divided by reactants, right?
हाँ मैंने K equilibrium, right?
Okay.
मैंने बस वो किया कि ना वो लिखना मुश्किल था ना, मैंने उससे ABCD कर दिया ना.
Yeah,
ठीक है.
okay.
अच्छा, so I'm going to call water X. ठीक है, so it's 4X. I think he's basically asking the equilibrium 4 constant, you have to describe it in terms of K stab 2 and K stab 3. So what I am calling X. So E and I already called that B, but over here I called it B, so I'm gonna keep it B. CdH2O6, is there CdH2O6? That's not there, so I'm gonna call it I'm gonna give it another name. I'm gonna call it Y. So CdH2O6 is Y. CH3NH2, what did I call it? I call it D. So I'm gonna give it the same name. I'm gonna call it 4D. And CdEN2H2O2, that's C. Achha, so K stab 3 is what? K stab 3 is C times X to the power 4 divided by Y times B to the power 2, right? And what's K stab 2? That's its expression is A times X to the power 4 divided by Y times D to the power 4, right? So I have these two expressions. So how do I combine K stab 2 and K stab 3 so that I get this thing? But how should I multiply? Should I divide that? Uh, how can I use K stab 2 and K stab 3 to give you the equilibrium expression for equilibrium number 4? Ibrahim, क्या करेंगे? I mean, I think it's going to be, but do you understand the question, right? Isaac, do you understand this?
A bit.
In 1 second. I mean the A, B, C, and D that I added over here, that was just added so that I could simplify things because the actual values were quite different. Uh, I think if I divide the two, what gets cancelled out? I think if I divide the two, the x to the power 4 will get cancelled out, the y will get cancelled out. So it's going to be c divided by b to the power 2, and that's going to be divided by a d4, right? Which if you know division, you can turn division into multiplication. The only thing you have to do is you have to switch the other side, right? So that comes down and this comes. And you can see I'm actually getting the same expression. So it's basically k stab 3 divided by k stab 2. I mean, k equilibrium over here, this expression over here is basically if you take the k stab 3 expression and you divide it by k stab 2 expression, you get exactly the equilibrium 4 constant. Is that clear? Ishaq, Qasim, Ibrahim, is this clear?
Yes, sir.
ठीक है, बस ठीक है. चलो ठीक है, we kind of you can go through the worksheet. I've sent you the worksheet. Uh, so I'm just going to see if there are more interesting questions, but most of the questions would all be about the ligand exchange that we wrote in the notes. There's not going to be anything. So tomorrow we'll just quickly go through if there's any interesting question, like the one that we just did. Most of the questions are just going to be exactly the same what we wrote in the notes. Okay? So we're going to start with a different topic tomorrow. Okay?
Okay,
Yeah.
sir.
Okay. Take care. Allah
Yeah.
Hafiz.